Okay, here will be your logic. Okay, so the distribution of all the same species is going to be like this, right? Appears to be a lot of things, but then this is just for your logic. When you set this down, then it's piece of cake algebra. So you get your total thing right there, right? It's 0.00250 molar, so it's going to distribute among all the possible zinc containing species, right? Will be written out like that. Okay, so solve one thing at a time. Solve for the equilibrium concentration of zinc. Free zinc. So start with this, call this your X. Okay, then the equivalent for the complex is like this, right? So you know how to write previously the B1 expression for that complex, right? Is equal to this. So the two multiply, three multiply each other, then you're going to replace that. Now here is the trick. Ammonia. Now your initial concentration is 0.50. Then at equilibrium, what is this concentration? Well, notice this is a limiting agent, the decimal places. So it's down to the third one. Yet ammonia is a high concentration. So after the reaction, it stays virtually the same. Virtually the same as 0.50. So unless you carry out more decimal places. But then in this case, 0.50 is 0.50. Okay, you end up with a equilibrium. So once you can see that, then this is the same as equilibrium concentration. So you throw that in. Okay, then B2, the equivalent for the second complex. B2 multiply that is equivalent to the second complex. Okay, so now plug in similarly 0.5 for ammonia and solve that X. Okay, so on and so forth for the fourth complex, the third complex. So now you just solve the X, right? So the X, plug in KF1, then this one is KF1, multiply KF2 from your table. Okay, then there's the 3 Ks multiply. Then here the 4 Ks multiply each other. Then be careful with the ammonia, the power. Okay, like that. So you can do the math. Yes?
How do you know the 0.50 is the excess? How do you figure that out?
Notice here, this is a limiting agent for zinc. It's so much lower when you have 0.05, in fact 0.5 for ammonia. So after reacting with a limiting agent, you're going to still have 0.5 molar. Okay, it's a relative magnitude comparison. Okay. Okay. So with this plugged in, then you're going to solve the uncomplex zinc. Well, it's virtually zero, right? Because all the Kf magnitudes are so big that they form the complex. Then you thought that, okay, the limiting agent, you're going to have none left behind. But the thing is, at equilibrium, there's two-way arrow. Okay, so that little tiny bit of reverse arrow going to give you back this little bit, 10 to the minus 11, zinc 2 plus. Okay, so it's not zero, absolute zero. Okay, once you found this, then what about the first complex? Then the first complex, then you just follow your expression up here, right? So this represents the first complex. Right here, the B1, multiply that and that. So you plug in this value into the X, and 10 to the minus 9 is that concentration. So now what about the second complex? The second complex is right here. Your label is B2, and plug in the concentration, then you're going to have the 2 complex, so on and so forth. Okay? Any questions? Okay. Okay, then another concept here is that competition reaction between complexation and precipitation. Now, for example, when you mix silver and cyanide, right? For complexation, then it can form the complex with a high Kf value of 10 to the 21st. Then it also can form precipitate. So you can look up the table for Ksp with this formula. Then is 10 to the minus 12. So now your question will be, if I mix the 2, then do I get precipitate or not, right? Notice the formula. This is charged molecule. So there's a molecular ion representing in solution. In solution, it may be a colored or a transparent solution, okay? But this indicates no charge is neutral, so this precipitate is going to go to the bottom of the solution. Okay, so here is an example. If you have 50 ml of 0.200 molar sodium cyanide, okay, solution. Then you mix with 10 ml of 0.100 of silver nitrate. Mix the 2. Do you get a precipitate? Okay, so now you will exercise your knowledge. Reaction is based on number of moles. So whatever the volume, concentration, then you want to calculate the number of moles here. Okay, and then the number of moles here as well. So that was calculated. So now you get the 2 relative amount. Then it appears that the cyanide has a large excess compared to this. Okay. So now the volume, concentration, right? Volume is a mixture, total. So which reaction is going to go first? Is going to be the formation reaction. Notice this is 10 to the 21. And this one, if you flip the reciprocal, is going to be the KL reaction. You know, your exam question. Okay, you reverse that, it's going to KL reaction. So you can say that that is KL reaction, the formation reaction, and this is a KL reaction for precipitate formation. So the reciprocal of this is about 10 to the power 13, right? Versus 10 to the power 21. So which one is going to react first? The formation reaction is going to react first. Until you have chemical left, then you consider the precipitation reaction. So proceed with that thought. Okay, so formation reaction, right? So formation reaction, you're going to form that product, right? So that product indicate is a silver CN2. The 2 should be outside of the bracket. I made a mistake of the 2 is inside the bracket. Okay, so from the 2 reactants, so we are looking at the overall picture. So we're going to use B2, so Kf1 multiply Kf2. Then how do we know it stops at that point? Because the table for silver and cyanide complex will give you the highest one is the 2 complex, okay? So that's how you know you use B2. So you go to that, so you calculate, because silver is your limiting agent, is 1 millimole only. So 1 millimole is going to form 1 millimoles of the complex. So the 2 should be outside the bracket again. So the CA, the 2 down here. So this concentration is equal to 1 millimoles over 60. Any question with this? 1 to 1, 1 millimoles, silver ion, all transformed into the complex. 1 to 1. So you get 1 millimoles over 60, that is a complex concentration. Okay? Then for the cyanide concentration, because the expression, right, you need to know all 3 concentrations. So the cyanide, to start with, was 10, right? 10 millimoles. 10 millimoles to begin with. Subtract 2. 2 is used to form this complex. Because 1 millimoles, right, the coefficient, 1 millimole here, then you will need 2 millimoles of Cn minus, right? 1 to 2. You are looking at the formula, right? This is 1, this is 2. And therefore, you consume 2. So at equilibrium now, what's left behind? 10 minus 2. Okay? So you get that concentration. So now, the free silver ion concentration, and plug back into the expression. Okay? Then you get this. This is really, really small, 10 to the minus 22, right? If that's 10 to the minus 24, then it would be single ion. That's a cool number, Avogadro's number, reverse. Okay? So this is a concentration left behind after formation reaction for silver, right? So now look at this quantity left behind and see if you get precipitate or not. Now KSP, cation and anion, KSP magnitude is like this. So your quotient, your experimental condition. So you have this quantity of free silver, 10 to the minus 22, and you have this quantity of the complex, which is up there, okay? So plug in, then you can visualize that the product here is going to be much less than KSP. So that means there will be no precipitate. You need to be at least equal to the KSP in order to precipitate off from solution. Okay, so there will be no precipitate. So exercise for you is right there, answer the question of whether you get precipitate or not. Okay, so as an exercise, your study group. Okay, that's it for today. See you in the lab.